Hi, thanks for joining me today. I've got another fun irrationality proof. I'm going to be proving that e, the very famous number in maths, is irrational. I'm going to be showing you the classic proof, which uses the definition that e is 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, and so on, that infinite sum there. Anyway, let's get stuck into the proof. Okay, so let's start off with the definition of e, this thing here, the sum of the reciprocals of the non-negative integers factorial, if that makes any sense. So 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, and so on, this infinite sum here. Now the first thing I claim is that e is not an integer. Okay, why is that? Well, clearly e is positive, so I claim that e is not a natural number. Well, this term here is 1, because 0 factorial is 1, so 1 over 1 is 1. This term here is also 1, so we get 1 plus 1. And these terms here are clearly strictly positive, so we get that e is certainly bigger than 1 plus 1, so e is bigger than 2. But I claim also that e is less than 3. In other words, this stuff here, so all the stuff after this 2 is less than 1. So this stuff here is less than 2, and that's not too difficult to see. Firstly, 1 over 2 factorial, that's equal to a half. Now 1 over 3 factorial, I can write this is the same thing as 1 over 3 times a half, because obviously 1 over 2 factorial is just a half, but 1 over 3 we know is less than 1 half, so this is less than a half, and then times that thing there, a half, which is 1 over 2 squared. Now with 1 over 4 factorial, so that's 1 over 3 factorial, 1 over 4 factorial, we can do a similar thing. This is equal to 1 over 4 times 1 over 3 times a half. But 1 over 4 is certainly less than a half, and a third is less than a half. So this thing here is less than 1 over 2 cubed. And then 1 over 5 factorial will be less than 1 over 2 to the 4, and so on. So this thing here is less than a half plus a half squared plus a half cubed plus dot dot dot. And this thing here is just 1. It's a geometric series which converges to 1. So that tells me that e is less than 1 plus 1 plus 1, which is 3. So I get that e is bigger than 2, but it's less than 3. So obviously e can't be an integer, because if it was, there'd be an integer between 2 and 3, and that of course makes no sense. Okay, so we've proved that e is an integer. Let me clean up the whiteboard and we'll continue with the proof. Okay, so we're going to prove that e is irrational by contradiction. So we're going to start off by saying, suppose for contradiction e is rational. So then we can write e in the form, let's say p over q, where p and q are clearly both, I mean they could both be negative, but we wouldn't want to write them as negative. We're going to assume that they're positive integers. So p and q are natural numbers, and of course q can't be 0, otherwise this makes no sense. But we also know that q can't be 1, because if q was 1, then this would just be an integer, but we've just shown that e isn't an integer. So we have that q is bigger than or equal to 2, and yeah, we'll also have, without loss of generality, that p and q are coprime, which is kind of standard, because if they're not coprime, we can just cancel them down. Right, so we have e equals p over q. So what I want to do is just plug this back into our definition up here. So just replace this now with p over q. And what I want to do now is multiply both sides by q factorial. Okay, so on the left hand side, I'm going to get pq times q factorial. Well, pq times q factorial, so p over q times q factorial. This thing here, q factorial, is precisely q times q minus 1 factorial. So I can actually write this thing here as just p times q minus 1 factorial. And that equals, on this right hand side, q factorial times this infinite sum here. Okay, but of course in this infinite sum we're eventually going to have a 1 over q factorial, because q is some natural number. So let's say it's there. Okay, and then of course we'll have a 1 over q plus 1 factorial, and so on, just squeeze it in there. Okay, so what I'm going to do is bring this to the top of the whiteboard and we'll continue. Okay, so let's continue. P times q minus 1 factorial equals q factorial times this infinite sum here. Let's just expand the brackets. This thing equals q factorial over 0 factorial plus q factorial over 1 factorial plus dot dot dot, all the way up to q factorial over q factorial. And the next term is going to be q factorial over q plus 1 factorial plus q factorial over q plus 2 factorial, and so on. Now, this stuff here is certainly going to be an integer. So all this stuff here is going to be an integer. Why is that? Well, q factorial over 0 factorial... Well, the denominator is always a multiple of the numerator. The numerator is a multiple of the denominator, because q factorial... Well, the bottom's just 1, so these are simple cases. But if, say, we look at q factorial over 4 factorial, provided q is bigger than or equal to 4, then q factorial is going to be q times q minus 1 times q minus 2, all the way down to 5 times 4 factorial. So when we divide by the 4 factorials, we're just going to get the 4 factorials cancelling, and we're still left with an integer. So each of these things here are integers, so when I add them up, they're certainly going to be an integer. I don't care what that integer is, I'm just going to denote it as t, where t is a natural number. Okay, so this stuff equals t, and now this stuff here I claim isn't an integer, and that's where we're going to get a contradiction. Why isn't this stuff an integer? Well, clearly it's positive. All these terms here are positive, so this thing here is certainly bigger than 0, but I claim that it's less than 1. Why is it less than 1? Well, let's look at the first term, q factorial over q plus 1 factorial. That thing there is going to be 1 over q plus 1. But we know that q is at least 2. So this thing here is going to be strictly less than a half. Because q is bigger than 2, so q is at least 2. So that means q plus 1 is at least 3. So that means 1 over q plus 1 is going to be at most a third, but that's still less than a half. Same thing for this thing here, 1 over q factorial divided by q plus 2 factorial, that's 1 over q plus 1 times q plus 2. And we're getting a similar thing to what we had previously. That thing there is going to be less than 1 over 2 squared. And the next term is going to be less than 1 over 2 cubed, and so on. So this infinite sum here, from here onwards, is going to be less than a half, plus a quarter, plus an eighth, plus a 16th, plus so on, which is in fact equal to 1. So this thing here is less than 1, but it's bigger than 0. So of course it can't be an integer, because otherwise there'd be an integer between 0 and 1, not including 0 or 1. Okay, so this thing here isn't an integer, but because this thing here is an integer, we get that this whole right hand side is not an integer. So with this right hand side here, whatever it is not an integer, because this thing here is an integer, but this thing here isn't. So if it were to be an integer, well, it just can't be an integer, because this is an integer plus something that isn't an integer, we're not going to get an integer. Okay, so the right hand side isn't an integer. Okay, so p times q minus 1 factorial we get is not a natural number. But obviously that's a contradiction, because q minus 1 factorial is certainly a natural number, as is p, so when we multiply them together we're going to get a natural number, but we don't. Okay, and that's where our contradiction comes from, so we can conclude that e is not rational and thus must be irrational. Okay, I hope you have enjoyed this proof, a very classic proof indeed. Unfortunately, you can't apply this sort of argument to pi. To prove that pi is irrational, it's a bit more difficult. Nonetheless, I hope you have enjoyed this video. Thanks for watching. I'll catch you in the next one. Have a great day.